This example here wants us to find the current density, right? So it's current density. It didn't specify which one, right? And that's given us the oxidation state, which basically is the N, right? But then here it says that even if it just says cathodic overpotential, we know this it should be negative, right? So we know we are done with the cathodic overpotential, right? So the current density we want us to find is the cathodic current density, right? Okay, so let's see. In order for us to do that, that will mean that we use the overpotential equation, right? Tafel equation, where we have this for the cathodic, right? The basic form is this, where we have this Tafel constant for cathodic half, and then we have log, and then we have I cathodic current density, and then we have current density, etching current density, right? Okay, so let's see. We have this, we don't have this, right? And then we have this as well. So let's find that. So the Tafel constant for the cathodic, we have a 2.303, right? NF on RT, right? RT on NF rather, RT on NF. So RT on NF. Yeah. Okay. But then let's pay attention to this. We've already come to understanding that. Let's go back to the graph. Right? It's actually the slope that ends up giving. It's actually the slope, right? That ends up making the whole potential negative. So that means that in anything that we do, it's only one of them that will make negative. So that will mean that it's either we make this cathodic positive and then we make this the BC negative, or we make this negative and we maintain this as how it is, right? In the calculation that we do, right? So looking at this one, the upper potential has already been given already negative, right? So if that has been given, meaning that we maintain this one here in positive, right? We maintain it in positive. So that's what we are doing. Okay, so let's see. What do we have for that? And that gives us oh boy. Let's see. Okay, and then we have a symmetry constant here, factor here, which is versus this is 1, ends up being 1 minus this, right? We said these are simple reactions, so the alpha is 0 0.5, right? So let's see, 2.303, right? And the temperature is 298, 25 to Kelvin is 298, and then the gas constant gas constant what is it? Okay, and then we have 1 minus 0 0.5, 0 0.5, and number of electrons involved is 1. That has been stated here, 1, right? So 1, and then we need the Faraday constant, right? Faraday constant, right? So that gives us this to be 0 0.11. Let's do 40p. 40p will make it 83 volts, right? Volts per decade, right? Per decade. Okay, so that's what we have for this. So now we have everything we need now to find the IC, right? So let's see. So we have this, which is minus 0 0.155, and then we have this, which is 0 0.1183, and then we have log, right? This is what we're trying to find. The etching current density is 5 times 10 to the power minus 7, right? Okay, so we'll be able to find our IC. So we have minus 0 0.155, 0 0.1183 log, and then we have, we're trying to find this, so we have 5 times 10 to the power minus 7, right? So let's see what we are getting for that. Alright, so that gives us the current density, the cathodic current density 0. Let's see, 1, 2, 3, 4, 5, 6, 7. Okay, 4, 5, 6, 7, 2, 4, 4, 8. Right. So when we change it to, if this were to be a normal calculator, we could have done it straightforward. Right. So 1, 2, 3, 4, 5, 6, 7, 8. Right. So we get 2.448 times 10 to the power minus 8. Right. And then looking at the unit for the exchange current density, right? So ampere per centimeter squared. So here we have ampere per centimeter squared, right? Yeah. So this is the answer we're having for this particular one. All right. So that's it.